Okay, so we're now doing exam review 3, question number 8. So you're told that you have a solenoid. So we have a solenoid, and it has to be a linear solenoid. So we have a core, and then we have this wire that wraps around the solenoid that's attached to a battery. Okay, and we're told that what are we told? We're told that the winding number, the number of windings per meter, right, that is wrapping around that solenoid is 3,400 windings per meter, so I'll just put meter per meter. We're also told the current I is given by 3.4 amps. You usually would put the units in, but I'm writing it out just to make sure you're understanding the idea. And find the magnetic field inside. And so the idea behind this, right, is that we're going to create a loop, a path loop, that basically is a rectangle. We'll say that this rectangle has a length L. Okay, and I'm going to create, so I'm assuming the magnetic field is in this direction. And so what the magnetic field, so remember, in solenoids, the basic idea in solenoids is that the magnetic field is really strengthened in the core of the solenoid, but it's zero outside. So really, in this region above and around the solenoid outside, the magnetic field is assumed to be zero. We're going to actually do a calculation where we don't have to assume this, and then actually notices that because the windings are so high, up to 4 significant digits, that magnetic field can be dropped down to assumed to be zero. So we're assuming that the magnetic field outside the solenoid is zero, and the magnetic field inside the solenoid has to be along the solenoid. So that's kind of good. But notice the magnetic field as we go from here to here is going to be zero. And so we can't use the first version of Ampere's law, which is basically B times L is equal to mu OI. So if B is uniform along some path, and I can multiply the perimeter of that length, I can multiply B times L to get mu OI. But we can't use that because the magnetic field is changing. So the second version of Ampere's law says that the sum of all of the line segments of magnetic field across some length I, the sum of all these paths, right? So if I have an eclectic path of elements like this, and here's my path, and each element, let's call this L1 vector, and this is the magnetic field along constant uniform electric field along B1, and this is B2 along from L1 to L2 vector, and this is L3 vector, and this is L4 vector, and so on. The magnetic field has, the sum of these dot products, right, is equal to mu O times the current that punctures the area that is bounded by this path. It doesn't have to be two-dimensional, this path, even though we just happen to have a path in 2 dimensions, right? Once I define a path, right, the surface could be any bounded. It could actually be a surface that goes outside this two-dimensional surface. I mean, the two-dimensional plane of this board. So this is mu OI. So we're going to do this calculation. So notice that if B and L are in the same direction, cosine of, remember, the dot product is of 2 vectors is the magnitude of A times the magnitude of B times cosine of angle theta. So if theta is equal to 0 degrees, they're in the same direction, this becomes 1. If theta is 90 degrees, cosine of 90 degrees is 0. So we don't have to worry about those elements. So let's go through this calculation. So the first segment, right, from here to here, B is uniform, so B dot L will be just BL. And then we have a segment that is not 0, but the length and the magnetic field, which is in direction, and the length that I'm going to calculate from here to here is 0, because the dot product of these 2 vectors are perpendicular to each other, so that's a 0. And once I go from here to here, from this segment, the magnetic field is supposed to be 0, and so that's 0 anyway. And along from here to here, the magnetic field is 0 anyway. So from here to here, before it reaches the actual windings, that is 0 also. And then from here to here, the length and the direction of the magnetic field are perpendicular, so that's 0. And all that is equal to so this is basically a rectangle, and we have how many puncturing of these wires have we gone through that surface, and that's equal to, well, let's see, mu o. The number of puncturings is n times the length, so the number of holes that this wire punctures that rectangular area, and how many times the current puncturing that each point is the current puncturing that, so it's n times L times I. So we have BL is equal to mu O times N times L times I. The L drops away, and this looks much like the solenoid equation. And so the magnetic field inside a solenoid, a linear solenoid, is given by mu O times the winding times the number of windings per meter times the current I. In this case, it's mu O is easy. It's 4 pi times 10 to the minus 7. Number of windings happen to be 3,400. The current is 3.4 amps, so standard units, so I don't have to do anything weird. And the units is in Teslas, T's. So that's the magnetic field strength inside a linear solenoid. But we're making sure that you're actually building it up from Ampere's law, building the answer up from Ampere's law.